It was nice. Since we don't have class this Friday, I want to make another video talk about introduce some computational complexity. So this is the short PowerPoint that I prepared for this classical computational complexity. Basically, this is like whole semester lectures. That's what the whole semester class. But I compress everything into one PowerPoint, and yeah, so this PowerPoint just for you to there are some keywords, right? There are a lot of things in this PowerPoint, but you just once you get this PowerPoint, if you find there are something interesting, then you can just directly go to find more resources. So I would say that maybe you don't understand this PowerPoint, the some concepts in this PowerPoint, but yeah, I mean, you can just directly find a resource. So yeah, so I would say this is somehow like a reference, and not this is not in the textbook. Okay. So what computational complexity means that this is somehow like a subfield in computer science called theoretical computer science. Okay, in the United States, there's a like one semester course. It's called computational complexity. But in Taiwan, I think it's hard to find such classes. Okay, but we have like only 1 week. Basically, we have only 1 hour, so I'll give you a quick tour and also come some lecture notes and some video links. So for you who are interested in doing like pure theoretical research, so I would say it's just a yeah, I mean it's fun. Hopefully you will change your life. Okay. Uh, okay. Wait. Okay. Oh, okay. So this is my personal perspective. So I think mathematics that I have learned some. So when I was graduate, I have learned some algebra geometry using some commutative ring, and then there's also a topic called additive combinatorics, which is very using some probability tool. I would say this is I believe from my perspective, I think algebra geometry is somehow like the most I would say in number theory, these are like most deepest thing in the mathematics. And in physics, that I learned the so-called quantum field theory and string theory. Maybe let me just remove this. Sure. Okay. So in physics, I learned some maybe you learn some quantum field theory, and maybe you learn some string theory, gravitational, Einstein general relativity. These are, I believe, that more abstract, like more I would say theoretical in the physics, right? But in computer science, I find that I believe that theoretical computer science and computational complexity somehow is the deepest thing in this topic. But why computational complexity in computer science that people like to solve the problem efficiently? So there's a course called algorithm, right? So philosophy behind the course algorithm is that people find a smart way to solve a computational problem looks hard. So there's a problem looks hard, but hopefully you find a smart way. So you have to learn in the undergraduate, right? Because there's a problem looks hard, but I mean, at school you learn some tool to solve it. Yeah, so this is a great textbook. And philosophy between algorithm, yeah, this is why it's for example, the problem looks hard, like sorting, like sorting is bad, how about like sort, so there are smart ways to solve it, right? So usually there's a tool like divide and conquer, dynamic programming, and there are so-called like default many interview questions, software engineering. But nowadays there's a AI tool, right? But in like 5 years ago, that many of PhD students are trying to spend their time trying to solve the code problem, and some of them are from math question that you can check online. So how about this complexity? So algorithm is that the problem looks hard, right? But there is a smart way to solve it. So complexity goes the way around, says that there are problems that are really hard in math. So it's yeah, we will say what it means in math rigorous way. But such that no matter how smart you are, you should not solve it in so let's solve it efficiently. So how can someone show such statement? And so this is why there's an idea called complexity classes. Okay, so one way to say is that complexity can be viewed as some anti-algorithm perspective. So there are two, yes, I say two categories. Now what you can do is algorithm, or something you may not be able to do is complexity. And if you want to understand the whole landscape, this Professor Ryan O'Donnell in CMU has two semester computation complexity. One is for undergraduate, one is for graduate, and there are a quick 1 hour lecture from MIT. So yeah, you can just directly find these videos. I would say this is very good. Yeah, you can learn a lot. Okay, so let's just say us about recall the so-called big O notation. So Fn GNB functions, then when I say Fn belongs to big O G of n, basically there is a number C and n0 such that Fn is bounded by upper bounded by C times Gn for n greater than n0. And then when I use small o, basically say that Fn is less than CG of n for n larger than n0. So it's upper, yeah, so, okay. And when I say omega, this big omega means the lower bound. So there exists a constant C and n0 such that Fn greater than C times Gn for n greater than 0. And there's a theta. So theta means that which is upper bound for which is big O and the big omega, basically mean that Fn and Gn are upper bounded by Gn and also lower bounded by Gn. So they have their scaling is up to constant, non-zero constant. Okay, so as I say in the previous lecture, that to define what computational mean, you need to first define a so-called classical computer, right? So you need to define a Turing machine, and you also need to know so-called languages. So languages are a subset of all bit strings of any length, and we use absolute value of x to define as a length of x. So language is a subset of all the bit strings. An algorithm basically decides the language. If x belongs to L, it should output 1. If x does not belong to L, it output 0. So algorithm is basically a classical, may not be classical, but if you define as classical complexity, basically define as a Turing machine. Okay. And then there's an idea called worst case complexity. The worst case complexity of a language L is the time required by best algorithm L of x decides L. Okay. And yeah, so hopefully this is well defined. Oh, I should open. Okay, and so once people define these languages and Turing machine, there's a long history, basically some long story behind this connected to pure mathematics. So for example, you can ask how many languages are there, and basically infinite for sure, right? But you know, in mathematics, there's a countable and uncountable, and it's easy to show that the number of languages are uncountable. And you can also how many codes or how many algorithms, how many classical Turing machine there, and basically it's countable. And then actually this is related to the three classes in the mathematics. You can try to find his history, and they involve some very big name like Cantor, Hilbert, Gödel, and Turing. And if you want to find some Mandarin text, Mandarin book for describing this, then I suggest this book. This is interesting. This is when I was high school. Yeah. And this is what I inspired by Professor Scott Aaronsen's talk that in complexity theory. So one can ask a question that why there's no such so-called rep drive or something which is you can jump to any timeline, right? But this is somehow like prohibited by so-called special relativity if you believe the speed of light is the upper bound of all the speed. And why there's no perpetual machine, because you know there's a so-called what the thermodynamics, right? So in thermodynamics, there's a law that you say that the whole system, the entropy of the whole system will increase, right? So there's no such magic devices in our universe. But so one can ask whether there's another like interesting machine that you can just put some mathematical question in and a well-defined mathematical question such that it will give you the answer. For example, like maybe you ask whether any even number greater than two can be written as sum of two primes. So for example, 4 is 2 by 2, 6 is 3, sorry, 4 is 2 times 2, 6 is 3 plus 3, and 8 is 5 plus 3, and sorry, not that, yeah, and 10 is 5 plus 5, right? So it seems like, okay, it's good. But, so this is famous Goldbach conjecture. The answer is we don't know. We don't know. But where there's a term, where there is a computer that you can just answer, and after some amount of time, some reasonable of time, you will output true. Okay. So if there's a some underlying physics law or some deep deep reasons why the previous two does not don't cannot exist in this universe, then maybe the third, right? So one can ask is third exists or not. Okay. So so this computability in the real world is that there's a various computer that people try to develop, and I will not describe the detail, but people try to use other kind of uh way to do computation. Right. So famous one is Church Cities. So this is a conjecture. So it says that all physical reasonable models computation have the same set of desirable functions. Okay, so basically, yes. So we believe that the Schrödinger series is correct. Okay, but there's okay. So notice that Schrödinger series only say computable. It have the same set of desirable functions. So it didn't. So this statement doesn't talk about the time. It didn't care about time complexity. You only care about whether this function can be computable. So computable meaning that you give a language L, there is an algorithm that can now, if you change your computational model, the set of languages that you can which you are desirable are fixed, no matter what kind of computer in this universe. Okay, so structure universities say that not only that, the complexity languages differ by at most polynomial factor between physically reasonable computational models. Okay, so what this means is that the complexity, the P, is solid. It's like robust. Under you, once you change the, even though you change the computational model. So this is the very deep conjecture that because you ask about the universe, right? So actually, I mean, you cannot prove it, but there's a challenge that's so-called what about quantum computing, right? And there's a extended so-called quantum treasure. See this is say that any physical reason model computation can be simulated polynomial time on quantum computer. This is also we are not sure. So what these statements say that quantum computer is the upper bound of this universe. That there's no more fancy computational model. And computer 2 may false like from like basically because we know that there's some problem that looks quantum computer can solve in polynomial time, but we don't know where classical computer can solve it. Okay, so inspired by all of this, then we can define a large sum of complexity classes like P and P exponential time, P space, and call P and P. So polynomial time, which is, let's say, input length is n, definition L in P if there is a Turing machine M, classical Turing machine M, such that if X in L, then M of X will run in polynomial time and output yes, or that true or what. Okay, so this means that this problem can be decidable in polynomial time, right? So if the answer is yes, then you will say, oh, it's yes, but spend only polynomial time. If X is not in L, basically mean that answer should be no, right? So M of X will run in polynomial time and output no. Oh, okay. So speaking P is a problem or language that can be decidable using classical computing in reasonable time, reasonable polynomial. Or polynomial time is defined to be less than equal to n to the C for some C greater than 0. Okay, so for example, sorting shortest path is most of the problem that you have there. Yeah, these are like breadth search, depth search. These are like some graph algorithms. And the exponential time that simple input is n, definition L is the same exactly, but runs in exponential time. Okay, so exponential bar is 2 to the c times polynomial in n. So 2 to the n, 2 to the n squared, 2 to the n cubed. Okay, so there's a theorem called time hierarchy theorem, which I will not prove here, but this is a very non-trivial proof. This is so-called diagonalization method. Is similar what Cantor proved that real number and the rational don't have the same cardinality. It's an interesting proof. Yeah. So exponential time is strictly larger than p. Okay, so p is different from xp. And then you can also define so-called double exponential time. And from time hierarchy, you can prove that double exponential time is larger than exponential time, strictly larger. So there's a infinite, I should say, infinite different complexity class. Right? So proof idea is basically using the Cantor's diagonalization theorem. And the rigorous treatment requires like one lecture to prove. Yeah, so I will skip here, but you can find the proof online. And there's another interesting class as we defined before, which stands for non-deterministic polynomial time called NP. So the input length is n, L in n. Okay, so this is L in NP. If there exists a Turing machine M such that if X in L, there exists a certificate of, or people call proof or witness, which is length of in terms of the length is poly X, so the length is reasonable. Okay, such that this Turing machine will take two inputs run X and Y runs in polynomial time and output yes. If X is not in L, then for all certificate of proof, M of XY will run in polynomial time and output no. So basically what this definition say that if somebody give you a magical Y, then you can solve it. And if the problem is no, then no matter what magical Y, you cannot solve it. So you will output no. So yeah, this is another definition. It's exactly the same, but just so called this M. Sometimes this M is called verified. So this is NP consists of all language L, which it is verified VXW such that VXW runs in polynomial time in X, and for all X in L, there exists the witness. So if the answer is yes, there exists a witness, then output yes. If the answer is no, then no matter what witness you have, you always get 0. So no, yeah. So this is no W satisfied equals to 1. So W is called witness or the certificate or the proof. A problem L is so, and once you have this NP, then you can define an idea called NP completeness and NP hard. So problem L is NP hard if every NP can be reduced to L. So a problem is L is NP complete if L is NP and NP hard. So this is called reduction, but the definition I will not give here. So NP complete. So there's an idea called NP completeness. So NP completeness can be seen as the hardest problem in NP. So if P is different from NP, then there's no polynomial type algorithm, worst case, to solve any NP complete problem, right? Because any NP complete problem can be reduced to NP complete problem. So there are many NP complete problems in this universe and also industry. So like covering satisfiable problem, traveling salesman problem, partition, and clique independent set. So you can find in like Nielsen, you can find maybe thousands of NP complete problems online, but there are like I remember that the original has like 23 problems that proved by Karp. So these are like interesting NP problems. Or actually, most of the problem that people care about is NP complete. This is weird that why this is true. And then there's another complexity class called BBP. So this stands for so remember that we say that one can define so-called randomized Turing machine, which is a Turing machine we can throw a coin in the computational step. So since it's throw a coin, right? So the output must be probability distribution. So the bounded probability polynomial time says that definition stands for BBP. Consists of all languages which there exists a classical algorithm AX such that A runs in polynomial time. And if X in L, then AX output yes with high probability. So high means that just two-thirds. Okay, and one can prove that two-thirds is just some number. If it's greater than, you can prove that if it's the same as, if it's you define as greater or equal to half plus some fixed amount. If x is not the same, not in L, then L of x output zero with high probability. And there's a conjecture that BBP equals to P. This is called de-randomization. And this is a very famous conjecture, and there are lots of work. Yeah, but I don't have time to talk about it. But I suggest that you read this Avi's oh, this is Terence Tao's blog describe what Avi's top is. So you can check about this. There's some of the videos by Avi that you can just find on YouTube, and also you can check out. So there's some non-trivial connection between this NP complete and BBP equals to P. Okay, and in textbook that you can check the so-called Chernow bounds. I will assign as a homework, but yeah. So what these results tell you that these two-thirds just these two-thirds is not important. You can change it to greater or equal to 80s, or whatever number greater than half, then you get the same class. Okay, so once you have this complexity idea, then one can define a P2P